receives. So in summary, I would like to demonstrate that our device is very fast, 10,000 times faster. Energy saving is more than 10 times. Endurance is 10 to 60, it's almost infinity. So something like this is very exciting, it's very interesting. And also 3D is stackable. You can make it 3D, so you can make it even more higher density. 10 layers, 100 layers. Nowadays, the company can make 96 layers. So you can see how is the density can make. So it's very important, yeah, very interesting. And also very interesting that could be last year, Intel Micron announced the so-called 3DX point. And they say the computing speed is 1,000 times. But till now, they never demonstrated real things yet. Yeah, real thing. They didn't demonstrate any real thing yet. No any sample yet. But I think they are still working on something interesting. I don't know what they are doing, but very interesting. They already announced. So I just give you some interesting news and flavor for you. People are working on this very hard. I think now it's a very competing world. Yeah, we are waiting. So now I would like to switch to another different topics. Okay. This principle not working for a small device like a 3 nano device or 7 nano device or 10 nano device. We can apply to a large area device. Large as maybe means a power device. Power device to control a high-speed train, control any kind of control the power grid, something like that. So this is for power device, large area device, and this principle can be applied not only for small device, it can also apply to large device. For power device, control large big power, megawatt power, something like that. This is our first demonstration on power device for the first time. We already made it. We already made it. This is a big device, large device. And still in the very beginning, so I cannot say we are very successful, but 65 millivolt per decade demonstrated. Still a little beyond a theoretical value, but it is even much better than the present device. Very high phase shift. And the on ratio is almost 10 to 9. So it's also very good. Yeah. So this is already we already at the beginning, which I first demonstrate initially, but we're still working on this. Hopefully we can make even better in a couple of months. Now I switch to another new device. This will be also will be demonstrate the coming conference in Hawaii in June. But this is a kind of 3-dimensional device, even higher density, maybe 100 layers we can make it, and with stackable, so make it a very high density. So we made it. How do we make it? So we use multi-layers, MP for maybe 100 layers, MP. And this is the other demonstration by P oxide, this kind of thing. In between is oxide, but we are using semiconductor consecutively. So this kind of concept can make it very good performances like this. So we have demonstrated that all those different layers, they are very uniform. But the previous one, POP, they are shrinking away. So it cannot be a multi-layers. So this kind of work doesn't work. But this kind of concept can make it very uniform and the many layers can be achieved. So something like this, and we already demonstrated good characteristics. Compared to POP, PN, or PNP is much better. These are our new structures, the new structures. And substrate swing is also close to the theoretical values, good. But the other three methods is even worse. And the uniformity we demonstrated is also very uniform, very controllable. Controllability is very good. This is not good, but this is good. And this is the temperature, high temperature characteristics from 0 to 200 degrees C, 200 degrees C. And our PNPN is very stable. Yeah, this one is no good because the temperature changes, the cell body changes quite a lot, but we are very stable differently. Yeah, very interesting. So different. So we also demonstrate a high temperature variation with a very small variation. This is only 2.4 millibart per degree, and this one is 4.7 millibart per degree, something like that. Yeah. So we promote that. This is another important thing that we demonstrate that the noise is much lower. Noise figure is very small. Noise figure is very noise. That's very important to have a signal over noise because you can make it a very small voltage and make a high efficiency, low power consumption. But noise is a very important factor, and we can make a lower noise with our structures, lower noise. So it's automatically lower. So it's so important in a signal processing. It's so important. So we can make a low noise even. Noise performance is even better. Yeah, something like that. Okay. So with the second internal gate, even we can control the threshold body, because a device we need it to be very versatile for high frequency, for frequency, for high power, for low power, which with the change of threshold voltage, we can control the threshold. The threshold can be tuned to our need. IoT need different kind of threshold voltage to fulfill different applications. Therefore, control the threshold voltage also very important, very critical. So we made internal gate to change the threshold voltage. Threshold voltage. I skip it. This is the threshold voltage change. Our structures can change from almost 0 volt to 1.2 volts. So this is a very large change of threshold voltage. That is very good for different applications, especially IoT, Internet of Things. It's very important to meet different applications using different threshold voltage. This is also important things we demonstrated, something like that. And also good thing is that we need a high on current. However, simultaneously, we need to lower the off current, because off current is standby power. It should be very slow, very small. So this curve shows that never any other group can show that on current increase, off current decrease. No other group can show that. Usually, you increase on current, simultaneously you also increase the off current. But we increasing on current, off current is similarly small, lower. This is another very interesting phenomenon. We can demonstrate it. Something like that. This is real noise figure versus different kind of structers, and this is lowest in our because we use a internal gate, and we enhance the current flowing through the perfect interface. Instead of upper interface is a lot of in the way trap, therefore very noisy. But we induce the current flowing, the perfect interface. Therefore, noise is significantly reduced. This is a principle we can explain why in our structure the noise is very much reduced. Okay, so finally I give you a summary of my present talk. We have demonstrated for the first time about the FET with the negative capacitance, with the high speed and the low noise, high efficiency, something like that. And with the negative, with the internal gate, we can demonstrate the FET with a high speed, low noise, and it's good, suitable for future post-Google era. So this is my summary. So I always say that it's time to reinvent the transistor. It's very important for the future post-Google, post-Apple, or post-Microsoft. It's very critical for the future. And we all nowadays we are collaborating TSMC to working on this kind of new technology. We are providing the good thing to the world in the next generation. We are very happy to say we are working together to doing something good for the world. Thank you very much.